Tonight, we're going to explore a beam of light older than the Earth itself, older than the Sun, older than almost everything you have ever known to exist. Somewhere out past the reach of ordinary sight, a single point of light has been travelling toward us for over 12 billion years. It left its source before our galaxy had finished forming. It left before there was a sun. It left before there was a you. By the end of tonight, you're going to understand exactly why this one distant star broke the rules scientists thought the universe had to follow. Billions of light years of darkness, and somehow, one flicker of ancient fire found its way to a mirror built here on Earth. But buried beneath that discovery is a truth that rarely gets mentioned. What Webb saw wasn't supposed to be possible. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Somewhere in that ancient light was a signature, a pattern, something that made scientists stop, look again, and question everything they thought they understood about the very first stars to ever burn in the darkness. Now let's begin. I want you to picture something with me. Close your eyes if it helps. Somewhere above you right now, past the ceiling, past the clouds, past the moon and the sun, and every star you could ever point to with your own eyes, there is a single point of light. It is faint, it is fragile, and it has been travelling toward Earth for longer than Earth has existed. Let that settle for a moment. Longer than Earth has existed. You and I are used to thinking of light as instant. You flip a switch, the room brightens, and that's the end of it. But out there, in the real universe, light takes time to travel. It has a speed limit, and when something is far enough away, the light reaching your eyes tonight isn't showing you what that place looks like now. It's showing you what it looked like when the light first left. Some of the light reaching Earth tonight left its source before there was an Earth to reach at all. This is the story of one such point of light, a single star so far away that the number describing its distance stops feeling like a number and starts feeling like a kind of poetry. Astronomers call it Earendel. You don't need to remember that name yet. What matters is this. When the James Webb Space Telescope turned its enormous golden mirror toward this speck of light, it wasn't just looking at a star, it was looking into the past, a past so deep, so ancient, that it edges up against the very beginning of everything. Here's the thing most people don't realise. When we say a star is old, we don't just mean it's been burning a long time. We mean the light you're seeing left that star roughly 12.9 billion years ago. 12.9 billion years. The universe itself is only thought to be about 13.8 billion years old. Do the math, and you start to understand what you're actually looking at. You are looking at light from a time when the universe was still a child. A time before galaxies had finished forming. A time before almost anything you have ever known existed in any recognizable form. And that's when it gets strange. Because when Webb finally gathered enough of this ancient light to study it closely, scientists expected to find something simple. A young, primitive star made of the most basic ingredients the universe had to offer in its infancy. What they found instead didn't fit. Something about this star's light told a story that shouldn't have been possible, not according to everything we thought we understood about how the first stars were built. We'll get to that. But first, I want you to sit with the sheer scale of what you're imagining. Think about the oldest photograph you've ever seen. Maybe it's black and white, a little blurry, a little faded, showing your grandparents as children, or a city street from 100 years ago. That photograph feels ancient to you. It feels like a window into a world that's gone. Now imagine a photograph so old that the people in it, the streets, the buildings, all of it, existed before your great-great-grandparents' great-great-grandparents were born, before your country was a country, before writing was invented. Now keep going. Keep multiplying that gap by thousands, then millions, then billions. That's the kind of window we're talking about. Except this window isn't made of paper. It's made of light itself, still travelling, still arriving, all these billions of years later. Complete silence is what surrounded this star for most of its journey to us. No radio transmissions passed near it, no spacecraft ever visited, no human eye had ever seen it directly. Not once, not for the entire span of human history, until a handful of scientists working with one of the most sophisticated instruments ever built finally caught its glow, and even then, they almost missed it. If not for a rare cosmic accident, a chance alignment of galaxies acting like a natural magnifying glass, this star's light would have been far too faint, far too distant for even Webb to detect. You'll understand exactly how that accident happened a little later in this journey. For now, just hold on to this feeling, the feeling of looking at something you were never supposed to be able to see. Why does this matter to you, lying there right now, eyes closed, listening to my voice in the dark? Because this story isn't really about a star, not entirely. It's about time. It's about how something impossibly old, impossibly distant, can still reach across the vastness of the universe and touch us here, now, on this small, quiet planet. It's about how the universe keeps secrets for billions of years, and every so often, almost by accident, lets one slip through. This is one of those slips, a crack in the darkness, letting ancient light spill through, carrying a message that scientists are still trying to fully decode. Before we go further, I want you to understand what kind of discovery this really is. This isn't a planet, a moon, or a familiar object simply seen more clearly. It's a message from an era of the universe that has otherwise vanished completely. The first stars, the very first generation, are believed to have lived fast and died young, burning out long before life of any kind existed anywhere. Finding one, seeing one, even indirectly, is almost like finding a fossil from the first day life appeared on Earth, except infinitely rarer and infinitely older. It rewrites what we think we know. It challenges assumptions that have stood for decades. And yet, here we are. A telescope built by human hands, launched into the cold of space, aimed with impossible precision at a single point of light most people will never hear about. It found something that made scientists pause, something that, once you understand it, might make you look up at the night sky a little differently than you did yesterday. Tonight, I'm going to walk you through exactly how this happened. From the birth of the universe itself, through the invention of a telescope built to peer into the past, to the strange and slightly unsettling truth hiding in the light of the oldest star we have ever seen. But to understand what makes this star so shocking, we first have to go back. All the way back before stars, before galaxies, before light itself had anywhere to travel. Back to the beginning of everything. That's where our story truly starts. Let's go back. All the way back, past every star you've ever wished on. Past every galaxy captured in every photograph you've ever admired. To a moment before any of it existed. 13.8 billion years ago, there was no space to speak of, and no time either. Not in any way you or I could recognize. There was no darkness, because darkness requires a place for light to be absent from. There was simply nothing, and then, in an instant too small to measure, everything began. Scientists call it the Big Bang, but I want you to forget the explosion imagery that name conjures. This wasn't a bomb going off in an empty room. It was the birth of space and time themselves, expanding outward from everywhere at once. In those first fractions of a second, the universe was smaller than an atom, and hotter than anything that has existed since. We're talking about temperatures with so many zeros after them that the number stops meaning anything practical. It's just heat, pure and absolute, beyond anything you could imagine standing near. And then, impossibly fast, that tiny searing point began to expand. Not into something, it simply grew. Space itself stretched, carrying the seeds of everything that would ever exist along with it. You, me, this planet, every star Webb has ever photographed. All of it was there, compressed into that first blinding instant. For a long time after that, the universe was too hot and too chaotic for anything solid to exist. No atoms could form. Particles moved so fast and collided so violently that nothing stable could survive more than an instant. Imagine a kitchen so hot that ingredients can't even combine into batter. They just burn apart the moment they touch. That's roughly what the early universe was like, on a much grander scale. It took hundreds of thousands of years, an unimaginable stretch of time by human standards, but a mere blink in cosmic terms, for things to finally cool enough for the first simple atoms to form. Hydrogen, a little helium, that was it. That was the entire recipe. And then came something scientists now call the cosmic dark ages. I want you to really absorb this phrase because it's not poetic exaggeration. For hundreds of millions of years after the Big Bang, the universe was genuinely dark. There were no stars yet to produce light. There was only a vast cooling fog of hydrogen and helium gas drifting through the newly formed fabric of space, utterly without illumination. No sunrise, no starlight, no glow of any kind anywhere for hundreds of millions of years. It is one of the strangest facts about our origins. The universe existed for a staggering length of time before it ever produced a single point of light. Complete darkness. Not the darkness of a moonless night on Earth, where starlight still filters down from countless distant suns. This was darkness with no exceptions anywhere. No candles waiting to be lit. No light switches waiting to be flipped. Just gas, drifting slowly through the cold, silent expanse of a universe still learning how to become something. If you'd been floating out there somehow, watching it happen, you would have seen nothing at all. Not because your eyes weren't working, because there was truly nothing yet to see. But gravity doesn't rest, even in the dark. Slowly, almost imperceptibly, tiny irregularities in the density of that primordial gas began to matter. Regions that were ever so slightly denser than their surroundings pulled in more material, growing heavier, growing denser still. Over millions of years, these regions collapsed further and further inward, gas gathering into ever tighter, hotter clumps. You can think of it like flour slowly clumping together in a bowl when dampness spreads through it unevenly. Except this process played out across unimaginable distances, gas gathering itself into the first true structures the universe had ever produced. Here's the thing most people don't realize about this process. It wasn't fast and it wasn't gentle. It took an enormous amount of time and an enormous amount of gravitational pressure before anything happened. But eventually, deep within these collapsing clouds of hydrogen and helium, the pressure and heat at the core became so extreme that something extraordinary occurred. Atoms began fusing together. Hydrogen nuclei collided with enough force to merge into helium, releasing a burst of energy in the process. That release of energy is what we call starlight. And in that moment, for the very first time since the birth of the universe, light existed. Try to imagine what that must have looked like, if there had been anyone there to see it. After hundreds of millions of years of absolute darkness, a single point of light flickers into existence somewhere in the vast cold emptiness. Then another. Then another. Slowly, scattered across the universe, these first stars began to switch on, one by one, like distant lanterns being lit in an endless black room. Scientists refer to this era as cosmic dawn. It is, quite literally, the moment the universe first learned how to shine. These earliest stars were unlike anything that exists today. They were built from almost nothing but hydrogen and helium, the only elements that existed at the time. No carbon, no oxygen, no iron, none of the heavier elements that make up planets or oceans or you. Just the simplest possible ingredients, burning under gravity's relentless pressure. And because of that simplicity, scientists believe these first stars were monstrous, far larger, far hotter, and far shorter lived than the stars we're familiar with today. Some may have been hundreds of times more massive than our own sun. They burned bright and they burned fast. Why does any of this matter to the story I'm telling you tonight? Because the star at the centre of everything we're exploring, the one Webb managed to see, may be a survivor, or a relative, or perhaps something stranger still, connected to this very first generation of stars. To understand why its light shocked scientists, you first have to understand just how empty, how dark, and how young the universe still was when the first stars ignited. You have to understand that finding light from this era isn't just rare. It's almost like catching a whisper from the very first voice the universe ever had. And that whisper, it turns out, had something unexpected to say. For decades, the first stars in the universe existed only in equations. No telescope had ever seen one. No photograph had ever captured their light. They lived entirely in the minds of physicists, built out of mathematics and careful reasoning, a theoretical population scientists simply called Population 3. You don't need to remember that name either, but I want you to understand what it represents. It represents a generation of stars so old, so primitive, and so far away that most astronomers assumed we would never actually see one. Not with any telescope, not in our lifetimes, perhaps not ever. Here's why these stars were considered almost mythical. Everything we understand about how stars form and behave today is based on stars like our own sun. Stars built from a rich mixture of elements. Hydrogen, yes, but also carbon, oxygen, nitrogen, iron, and dozens of other elements scattered throughout the clouds of gas that stars are born from. Those heavier elements matter enormously. They change how efficiently a forming star collapses, how hot it burns, how long it lives, and even how large it can grow. But the very first stars had none of that richness available to them. They were born from a universe that hadn't yet learned how to make anything but the simplest atoms. Think of it this way. Imagine trying to bake bread, but the only ingredient you have access to is flour. No salt, no yeast, no water beyond the bare minimum. You could still make something, technically, but it would behave very differently than a fully developed recipe. That's roughly the situation the first stars faced. Built almost entirely from hydrogen and a touch of helium, with none of the heavier elements that make star formation easier and more controlled, these stars are believed to have formed under extreme, almost violent conditions. Gravity had to do all the work alone, with none of the usual help. The result, according to decades of theoretical modelling, would have been stars of almost unimaginable size. Some models suggest population 3 stars could have grown to hundreds of times the mass of our Sun, and possibly more. To put that in perspective, if you replaced our Sun with a star like this, its outer layers might stretch out past the orbit of Mercury, past Venus, potentially engulfing Earth's orbit entirely. These weren't stars in the gentle, familiar sense. They were furnaces on a scale that modern stars simply don't reach. And because they were so massive, they burned through their fuel violently fast. A star like our Sun is expected to shine steadily for about 10 billion years. The very first stars, by contrast, may have burned for only a few million years before collapsing catastrophically. In cosmic terms, that's barely a flicker, a candle burning impossibly bright for a heartbeat, and then gone. When they died, many are thought to have exploded as supernovae so powerful they scattered heavy elements across the surrounding universe for the first time in cosmic history. In a very real sense, these dying giants created the raw materials for everything that came after, including planets, including oceans, including you. Here's the thing most people don't realize. Almost everything you're made of, the calcium in your bones, the iron in your blood, the oxygen in every breath you take, was forged inside a star that lived and died long before Earth existed. The first stars didn't just light up the darkness. They manufactured the ingredients of life itself, then scattered those ingredients outward in violent death, seeding the universe for everything that would eventually follow. Without their brief, explosive existence, none of the complexity we now take for granted would have ever been possible. But despite how important these stars are to the story of everything, actually seeing one has remained almost impossible. They existed too early, too far away, and burned for far too short a time. By the time telescopes powerful enough to look that deep into space were developed, the very stars scientists most wanted to study were long extinct. Their light either extinguished entirely, or so faint and so redshifted by the universe's ongoing expansion that it should have been undetectable. For years, hunting for direct evidence of population 3 stars felt a bit like searching for footprints from a storm that ended before anyone arrived to see it. This is where the story starts to bend towards something extraordinary. Because while nobody expected to see an actual first-generation star with their own instruments, some astronomers held on to a quieter hope, not of seeing a true, pure population 3 star exactly as it burned in the earliest days of the universe, but of catching something close, a star old enough, primitive enough, that studying it might offer a rare, almost accidental glimpse into that vanished era. A messenger, carrying clues from a time otherwise lost to darkness and distance. And that's precisely the kind of discovery that eventually led scientists to the star at the heart of tonight's story. Not necessarily one of the true original giants that once lit up the cosmic dark ages, but something old enough, strange enough, and distant enough to raise an unsettling question. What if some of our assumptions about those very first stars were wrong? What if the universe's earliest chapter wasn't quite as simple or as tidy as decades of theory had suggested? To even ask that question, scientists first needed a tool capable of reaching that far back in time. Not just a powerful telescope, but one specifically engineered to detect the faintest, most ancient light imaginable, stretched and dimmed by billions of years of cosmic expansion. That tool didn't exist for most of human history. It took generations of engineering, decades of planning, and one of the most ambitious space missions ever attempted to finally build something capable of looking that deep into the past. In the next chapter, I want to introduce you to that telescope and to the extraordinary story of how humanity built a machine specifically designed to stare into the beginning of everything. To understand how anyone could ever see a star from the dawn of time, you first have to understand a simple but strange fact about light. The farther away something is, the older the light you're seeing becomes. But there's a second layer to this fact, one that's a little harder to picture. As the universe expands, the light travelling through it gets stretched along the way, like a wave pulled gently across a growing surface. This stretching shifts light toward longer, redder wavelengths, a phenomenon scientists call redshift. The most ancient light in the universe isn't just faint. By the time it reaches us, it has been stretched so far that it barely resembles visible light at all. It arrives instead as infrared, a wavelength human eyes were never built to see. This single fact created an enormous problem for astronomers hoping to look back to the very beginning. Ordinary telescopes, even extraordinarily powerful ones, are built primarily to capture visible light, the same kind of light your eyes use every day. But the light from the earliest stars and galaxies doesn't arrive as visible light anymore. It arrives almost entirely in the infrared, shifted far beyond what most instruments were ever designed to detect. If humanity wanted to see that far back, it wouldn't be enough to build a bigger telescope. It would require an entirely different kind of instrument, engineered specifically to capture light that had been stretched almost beyond recognition. That instrument is the James Webb Space Telescope. I want you to picture it for a moment, because its design is almost as remarkable as what it has managed to see. Unlike telescopes that use a single solid mirror, Webb's primary mirror is built from 18 hexagonal, gold-coated segments, fitted together like an enormous honeycomb stretching more than 6 meters across. Gold specifically, because gold reflects infrared light with extraordinary efficiency, far better than ordinary mirrored glass. Every angle Every coating, every material choice was made with one purpose in mind: catching the faintest, oldest, most stretched out light the universe has ever produced. But a mirror alone wasn't enough. Infrared light is essentially heat, and heat is everywhere. Your own body gives it off. So does the earth beneath you, and the sun above you, and nearly everything around you right now. For Webb to detect the impossibly faint infrared glow of ancient starlight, it needed to be shielded from every other source of heat imaginable, including the warmth radiating from Earth itself. The solution engineers designed is almost poetic in its simplicity. A sun shield, roughly the size of a tennis court, made of 5 incredibly thin layers, unfolded in space like the wings of some enormous metallic moth, blocking out the heat of the sun, the Earth, and the Moon all at once. Here's the thing most people don't realize about where Webb actually operates. It isn't orbiting Earth the way older telescopes do, circling close by, alternating between sunlight and shadow every 90 minutes or so. Webb sits nearly 1 million miles away from Earth, at a gravitationally stable location called the second Lagrange point. Out there, shielded from the sun's heat, Webb's instruments can cool to temperatures colder than almost anywhere else humans have ever engineered. Some of its detectors operate at temperatures hovering just a few degrees above absolute zero, the coldest theoretical temperature that exists. Only in that extreme frozen stillness can Webb detect light faint enough to have crossed billions of years of expanding space. Building something this precise didn't happen quickly or easily. Webb's development stretched across more than 2 decades, involving thousands of scientists and engineers across multiple countries, and costing an almost unimaginable amount of money and effort. There were years of delays, there were moments when the entire project nearly collapsed under its own complexity. Unlike its predecessor, which could be physically repaired by astronauts. If something went wrong, Webb would be sent so far from Earth that no rescue mission could ever reach it. Every single one of its hundreds of individual mechanisms, every hinge, every mirror segment, every fold of that delicate sunshield had to work perfectly, the very first time, with no chance for human hands to fix a mistake. On Christmas morning, in 2021, that risk was finally put to the test. Webb launched aboard a rocket from French Guiana, carrying with it decades of hope, ambition, and quiet anxiety. Over the following weeks, in a process engineers nervously called the 129 deployments that could fail, Webb slowly unfolded itself in the vacuum of space, each mirror segment shifting into place, each layer of the sunshield stretching taut, millions of miles from any possibility of repair. Complete silence and complete trust were the only options available to the people watching from Earth. Every step succeeded. By the middle of 2022, Webb had reached its final position and cooled to its operating temperature, ready to begin its work. And almost immediately, it began delivering images unlike anything humanity had ever seen. Galaxies from the universe's early history, sharper and more detailed than anyone expected. Structures forming out of gas and dust in ways that reshaped scientific timelines almost overnight. But among the countless discoveries Webb was designed to make, one particular kind of target remained especially difficult, especially rare, and especially precious. Individual stars from the very edges of observable time. Here's why that's so difficult, even for a telescope this powerful. Stars are small. Galaxies are enormous, filled with billions of stars blended together into a single glowing shape from enormous distances. But a single star, even a massive one, is almost impossible to distinguish individually once you're looking billions of light years away. The light simply isn't strong enough, isn't concentrated enough to stand out clearly, even to an instrument as sensitive as Webb. For scientists hoping to study individual ancient stars rather than distant blurred galaxies, something extra was needed. A kind of cosmic assistance that no engineer could design or build. It would have to come from the universe itself. And remarkably, The universe had already provided exactly that, long before Webb ever launched. A strange, almost accidental phenomenon, hiding in plain sight, capable of magnifying distant starlight by extraordinary amounts. Astronomers had a name for it, and a growing understanding of how to use it. In the next chapter, I'll show you exactly how this cosmic accident works, and how it eventually led to the discovery that would leave scientists staring at their screens, quietly stunned, in 2022. Every great discovery has a moment attached to it, a specific point in time when the unknown quietly becomes known. For the star at the centre of tonight's story, that moment didn't begin with Webb at all. It began years earlier, in 2016, with an older telescope and a photograph that almost nobody thought twice about at first. Buried within an image captured by the Hubble Space Telescope was a faint, barely visible smear of light stretched across a distant cluster of galaxies. To most observers, it would have looked like nothing more than a flaw, a smudge, an artifact easily overlooked. But to the astronomers studying it carefully, that smear told a very different story. The smear appeared along something scientists call a caustic, an extremely precise, knife-thin line, created by an effect known as gravitational lensing. Here's the simplest way I can describe it to you. When light from a very distant object passes near something incredibly massive, like an entire cluster of galaxies, the intense gravity of that mass bends the path of the light around it. It's a little like looking through the base of a glass, where the curved surface bends and magnifies whatever sits behind it. In rare, perfectly aligned cases, this bending doesn't just distort the light, it amplifies it, sometimes by a factor of thousands, allowing astronomers to see things that would otherwise be far too faint and far too small to detect at all. The massive galaxy cluster responsible for this particular alignment is known as WHL 137-08. Sitting between Earth and the distant point of light, its enormous gravity acted almost like a naturally occurring magnifying glass, stretching and brightening the light passing behind it along one precise narrow line. Astronomers gave that thin, glowing thread a fitting nickname, Sunrise Arc, and somewhere along that arc one point of light stood out, brighter, sharper, more concentrated than anything around it. It didn't look like an entire galaxy smeared across the sky. It looked like something closer to a single point, something that might, almost impossibly, be an individual star. The team studying this discovery gave it a name drawn from Old English, meaning morning star or rising light. Earendel. At the time, using Hubble alone, scientists could tell the object was extraordinarily distant and extraordinarily magnified, but they couldn't yet determine exactly what it was made of, or precisely how old it truly was. Hubble had found the signal. It had proven something extraordinary was hiding along that thin arc of light. But answering the deeper questions, the questions that would eventually shock scientists, required something far more sensitive. It required an instrument built specifically to analyze faint, ancient, deeply redshifted light in extraordinary detail. It required Webb. In 2022, not long after Webb became fully operational, astronomers pointed its instruments directly at that same narrow arc of magnified light. This time, they weren't just hoping to confirm that something was there. They were hoping to finally read its story. Using an instrument capable of splitting incoming light into its individual wavelengths, a technique known as spectroscopy, scientists could begin to determine the object's temperature, its composition, and crucially, its true distance and age. It's a bit like taking a single beam of white light and passing it through a prism, revealing the hidden rainbow of colours folded inside, except this rainbow would reveal secrets about the birth of the universe itself. What came back from those observations left the research team quietly stunned. The data confirmed that this point of light wasn't a small cluster of stars or a compact clump of stellar material, as some had initially suspected. Everything about its light pointed to something remarkable, a single star or at most a very small handful of stars, magnified by thousands of times through gravitational lensing, its light stretched across nearly the entire history of the universe to reach us. The distance calculations placed it at a redshift, indicating its light had been travelling for approximately 12.9 billion years. 12.9 billion years, arriving now tonight into an instrument built by human hands, less than a century into our species' effort to understand the stars. Here's the thing most people don't realise about a discovery like this. For most of human history, individual stars beyond our own galaxy simply couldn't be observed this way. Entire galaxies, yes, clusters of millions of stars blurred together into a single glow, certainly. But one star, isolated, magnified, and studied in this kind of detail from a time when the universe was still less than 1 billion years old, that had never been done before. Earendel instantly became the most distant individual star ever detected, shattering the previous record by an enormous margin. It wasn't simply a new data point, it was a new category of discovery entirely. I want you to imagine the room where this realization first settled in. Screens filled with numbers, spectral graphs, faint curves of light plotted against wavelength. And somewhere in that data, a team of scientists slowly recognizing what they were actually looking at. Not a blur, not an approximation, an individual star, its light having survived a journey across nearly the entire breadth of cosmic history, arriving intact enough to be studied, measured, and questioned. There's a particular kind of quiet that settles over a room in moments like that. Not celebration exactly, something closer to disbelief, but confirming Earendel's extraordinary age and distance was only the beginning of the story, not the end of it. Because once scientists began digging deeper into the details of its light, something didn't sit right. The spectrum, the very same tool that had confirmed just how ancient and how distant this star truly was also quietly revealing something else. Something that didn't match the simple, primitive picture scientists expected from a star this old. Something buried in the light itself, waiting to be noticed. And once it was noticed, it would completely change how astronomers thought about this discovery. That's where our story goes next. I want to slow down for a moment and really introduce you to Earendel, not just as a data point or a record-breaking distance, but as an object, a star. Something that, in some form, actually exists, or once existed, at the far edge of everything we can observe. Its name comes from Old English poetry, referring to a rising light, a morning star, something that appears at the boundary between darkness and dawn. It's a fitting name, because in many ways, that's exactly what this star represents. A boundary, the edge of what our instruments can see, and the edge of what we thought we understood. Here's the thing most people don't realize about how astronomers actually estimate what a star like this might look like. Nobody has a clear photograph of Earendel's surface. Nobody ever will. Even magnified thousands of times by gravitational lensing, the star remains an unresolved point of light, a single glowing dot rather than a detailed image. Everything scientists know about its size, its temperature, and its mass comes from careful analysis of that one faint signal, compared against decades of models describing how stars of different types behave. It's a bit like identifying a person from a single distant silhouette, using their outline, their posture, and the quality of the light around them to make educated, careful guesses about who they are. Based on that analysis, scientists estimate Earendel is significantly more massive than our own Sun, likely somewhere between 50 and a few hundred times as massive, and possibly hundreds of thousands of times brighter. To put that brightness into perspective, imagine every star you can see with your naked eye on a clear night, combined together and still falling short of the light pouring out of this single, ancient object. It's the kind of number that stops feeling like a measurement and starts feeling almost abstract, a brightness so extreme that ordinary comparisons start to break down. But brightness and mass alone don't explain why scientists were able to see it at all. For that, we have to return to the gravitational lens responsible for this entire discovery. The massive cluster of galaxies sitting between Earth and Earendel, bending and magnifying its light along that narrow glowing thread called the sunrise arc. Here's a detail that makes this discovery feel even more delicate, almost improbable. For the magnification to work as precisely as it did, Earendel had to sit almost exactly along the caustic, the razor-thin line of maximum lensing distortion. A little too far to one side, and the magnification would have been far too weak to detect. A little too far to the other side, and the light might have been split into multiple separate images instead of concentrated into one. Astronomers estimate that this alignment magnified Earendel's light by a factor of at least 1,000, and possibly as much as 40,000, depending on exactly how close to that precise line the star truly sits, 40,000 times brighter than it would otherwise appear to us. Without that magnification, this star's light would have been far too faint for even Webb's extraordinary sensitivity to detect. In other words, seeing Earendel wasn't simply a triumph of engineering. It required an extraordinary, almost unrepeatable coincidence of cosmic geometry, a fleeting alignment between Earth, a massive galaxy cluster, and a single ancient star, persisting just long enough and precisely enough for us to notice. Think about what that actually means. Somewhere in the vast star-filled emptiness of the early universe, countless other ancient stars almost certainly exist or once existed, just as bright, just as extraordinary as Earendel. But without a similar, precise gravitational alignment working in our favour, their light remains completely invisible to us, hidden not by distance alone, but by simple bad luck of geometry. Earendel isn't necessarily unique in what it is. It may simply be extraordinarily fortunate in how it happened to be positioned, relative to us, at exactly the right moment in cosmic history for its light to become detectable at all. There's something almost unsettling about that realization, isn't there? An entire hidden population of ancient stars scattered throughout the early universe, and we've only managed to glimpse one of them purely by chance. Not because we searched more carefully than anywhere else, not because this particular patch of sky is special in any fundamental way, simply because at this exact moment in cosmic history, the geometry happened to align. It's a humbling thought. For all of Webb's extraordinary engineering, for all of humanity's careful calculation and decades of preparation, this discovery ultimately depended on a stroke of pure cosmic luck. Here's another detail worth sitting with. Because of the extreme distances and timescales involved, Earendel almost certainly no longer exists in the form we're observing it. Stars this massive burn through their fuel extraordinarily quickly, often surviving only a few million years before ending in a catastrophic collapse or explosion. Given that the light reaching us left this star roughly 12.9 billion years ago, it's overwhelmingly likely that Earendel, in whatever form it once had, met its end long before the light revealing its existence ever reached Earth. In a very real sense, we are watching a ghost, a star that may have stopped existing billions of years before humanity even evolved to look up and notice it. And yet, that ghost still has something important to tell us. The light Webb captured wasn't just a confirmation of distance, or size, or brightness. Hidden within its spectrum was chemical information, subtle signatures revealing what elements this star was actually made of. For a star this ancient, this close to the very beginning of cosmic time, scientists expected a simple answer. Mostly hydrogen, a touch of helium, the bare minimum ingredients available in the universe's earliest days. What they found instead didn't match that expectation cleanly, and that mismatch, subtle at first, then increasingly difficult to ignore, is where this story takes its strangest turn. Before we go further into what scientists actually found hidden in Earendel's light, I want to pause here with you and really sit with the distance involved. Not just as a number, but as something you can actually feel. Because numbers this large have a strange effect on the human mind. They stop registering as quantities and start registering as something closer to abstraction. And I don't want this one to slip past you that way. So let's slow down and build it piece by piece. You already know that Earendel's light has been travelling for roughly 12.9 billion years. But light moves fast, almost incomprehensibly fast. It travels at about 186,000 miles every single second. In the time it takes you to blink, light could circle the entire Earth several times over. And yet, even moving at that almost unimaginable speed, without pause, without slowing down, even once, it still took nearly 13 billion years for this particular beam of light to cross the distance between Earendel and us. Let's turn that into miles because the number deserves to be said aloud. Light travels roughly 6 trillion miles in a single year. Multiply that by 12.9 billion years, and you arrive at a distance so large it stretches far beyond 70 quintillion miles, 70 followed by 18 zeros. I could repeat that number to you slowly, digit by digit, and it still wouldn't quite land the way it should, because the human mind was never built to hold distances like this. We evolved to judge the distance across a valley or a coastline, not the distance across the birth of time itself. Here's a way to make it a little more real. Our own sun sits about 93 million miles from Earth, and even that distance is difficult to fully picture. Light from the sun takes about 8 minutes to reach us. Now imagine trying to count, minute by minute, all the way up to 12.9 billion years. You would run out of every measuring tool humanity has ever invented long before you finished. Entire civilizations could rise and fall, entire species could evolve and vanish, and you would still be counting. But speed and distance are only half the story. Remember what we discussed earlier about the universe's ongoing expansion. Earendel's light hasn't simply travelled an enormous distance through fixed static space. It has been travelling through space that is itself expanding, stretching, growing larger the entire time that light moved through it. Because of that expansion, the actual physical distance to whatever remains of Earendel today, assuming anything remains at all, is now estimated to be somewhere around 28 billion light years away. Not 12.9, 28 billion. The universe grew even as the light was crossing it. Here's the thing most people don't realize about what this actually means for you right now, listening to my voice in the quiet dark. When you look at Earendel's light, you're not seeing where that star is today. You're seeing a fossil, a frozen record of a single moment, preserved in light from an era so early in cosmic history that our own solar system hadn't even begun to form. Earth wasn't a swirling cloud of dust yet. The sun hadn't ignited. There was no place for you to eventually exist, and yet this light was already on its way here, patiently crossing billions of years of empty space, long before there was anyone waiting to receive it. Almost everything is missing from that early universe compared to the one we know today. No solar system, no Milky Way in its current form, no familiar constellations. The universe Earendel's light departed from would have been almost unrecognizable, filled with young, chaotic galaxies still forming their basic structure, illuminated only by the earliest generations of stars scattered sparsely across an otherwise mostly dark cosmos. And somewhere within that unfamiliar, ancient landscape, a single point of light began a journey that would eventually end here, on a small planet, inside an instrument built by creatures that hadn't even evolved yet. I want you to consider something else, something quietly humbling. Every photon of that light travelled uninterrupted, undisturbed, for nearly 13 billion years, until it finally struck the golden mirrors of the James Webb Space Telescope. No obstacle stopped it, no collision scattered it. It simply travelled silently, patiently, across almost the entire history of everything, waiting for a receiver sophisticated enough and patient enough to finally catch it. Out of the near-infinite darkness of space, that fragile beam of light found its way to exactly the right instrument, at exactly the right moment, after a journey longer than almost anything the human mind can properly comprehend. And yet, for all that distance, for all that time, the light still carried information. Real, measurable information about the star it came from, its temperature, its brightness, and most importantly for our story, the specific chemical fingerprints of the elements burning within it. That information didn't get lost somewhere along those 70 quintillion miles. It survived the entire journey, intact enough for scientists to study it in extraordinary detail. And when they finally did study it closely, that information told them something that didn't fit the simple story anyone expected. Something that felt, to more than one scientist reviewing the data, almost impossible. I want to bring you into the process now, not just the result, but the actual methods scientists use to pull meaning out of a single point of light billions of years old. Because it's one thing to say, Webb detected a star. It's another thing entirely to understand how a beam of light, faint and ancient and stretched nearly beyond recognition, can be turned into detailed information about temperature, composition, and age. The tool responsible for that transformation is called spectroscopy, and it is, in many ways, the quiet hero of this entire discovery. Here's the simplest way I can explain it. Every element in the universe, when heated to extreme temperatures, absorbs and emits light at very specific, very precise wavelengths. Hydrogen has its own particular pattern. Helium has another. If heavier elements are present, each one leaves its own distinct signature as well. When starlight passes through a prism, or through the sophisticated instruments Webb carries on board, it doesn't just spread out into a smooth rainbow. It spreads out into a rainbow interrupted by thin, precise lines, dark or bright depending on the process involved, each one corresponding to a specific element. It's a bit like a fingerprint. No two fingerprints look identical, and no two combinations of elements produce quite the same pattern of lines. For a star as distant and as ancient as Earendel, capturing a clear enough spectrum to read these fingerprints was an extraordinary technical challenge. The light arriving at Webb's instruments was already impossibly faint, magnified only by that fortunate gravitational alignment we discussed earlier, and further stretched by billions of years of cosmic expansion. Every wavelength had shifted dramatically toward the infrared, meaning scientists weren't just looking for familiar patterns, they were looking for those same patterns, shifted, stretched, and dimmed, hiding somewhere within an ocean of infrared noise. It required extraordinary precision and an extraordinary amount of patience. When the data finally came back clearly enough to analyze, the initial findings lined up, at first glance, with expectations. The spectrum confirmed an extremely hot, extremely luminous object, consistent with a massive, early universe star. The temperature estimates suggested something blisteringly hot, potentially exceeding 20,000 degrees at its surface, hot enough to glow with a fierce blue-white intensity far beyond anything our own sun produces. Millions of degrees deeper within its core, if current stellar models hold true. Everything about its brightness, its estimated size, its estimated mass, fit reasonably well within the range scientists expected for an early, primitive, massive star. But then came the deeper analysis, the kind that takes longer, that involves comparing the star's light, not just against simple expectations, but against detailed models built to simulate exactly what stars from this early era should look like, chemically. And that's where the picture started to become more complicated than anyone initially anticipated. The composition suggested by the spectrum didn't cleanly match what a truly primitive, first-generation star should contain. There were hints, subtle but persistent, of chemical complexity that shouldn't have existed yet, this early in the universe's history. Here's the thing most people don't realize about how sensitive this kind of analysis really is. We're not talking about obvious, dramatic differences visible at a glance. We're talking about faint signals, buried deep within noisy data, requiring careful statistical analysis to even confirm they're real, rather than simply an artifact of measurement error or gravitational lensing distortion. Scientists don't simply glance at a spectrum and declare a discovery. They run the data through multiple independent models, compare results across different research teams, and stress test every possible alternative explanation before drawing any conclusions. This process took time, it took careful, patient scrutiny, and through that patient scrutiny, something persistent kept emerging. Some analyses of Earendell's light suggested the presence of chemical signatures inconsistent with a purely primordial star, one built only from the simplest possible ingredients the early universe had to offer. There were indications, still debated among researchers, of elements that shouldn't have existed in significant quantities this early in cosmic history. Elements that typically require earlier generations of stars to have already lived, died, and scattered their remains through supernova before they could exist at all in meaningful concentrations. That's the contradiction sitting at the heart of this discovery. If Earendel truly formed as early as its distance and age suggest, deep within the universe's first billion years, there simply shouldn't have been enough time, enough previous stellar generations for these particular chemical signatures to exist yet. And yet, hints of exactly that complexity kept appearing in the data, refusing to fully disappear even after careful repeated analysis. It's the kind of contradiction that makes scientists lean closer to their screens and start asking harder questions. I want you to sit with that tension for a moment, because it's the quiet turning point of this entire story. A star sitting almost impossibly early in cosmic history, showing signs of chemical complexity that theoretical models say shouldn't be possible yet. Not proof of anything supernatural, not evidence of anything beyond natural explanation, but a genuine, persistent puzzle. One that forced scientists to reconsider some of their most basic assumptions about how the earliest stars in the universe actually formed, lived, and influenced everything that came after them. Here's the thing most people don't realize about scientific discovery in moments like this. It rarely arrives as a single, dramatic announcement. More often, it arrives exactly like this, quietly, gradually, as researchers slowly realize that their data keeps refusing to match their expectations, no matter how many times they check it. Something was there in Earendell's ancient light that didn't belong according to everything astronomers thought they understood about the universe's first stars. And once that anomaly became impossible to fully explain away, the real questions finally began. Let's slow down here, because this is the part of the story where things stop being simply extraordinary and start becoming genuinely strange. Up until now, everything about Earendel, its distance, its brightness, its staggering age, fit within the boundaries of what scientists expected to eventually find. Remarkable, yes. Record-breaking, certainly, but not contradictory. What came next was different. What came next was the kind of finding that makes a research team go quiet, then start double-checking their own work, just to be sure they hadn't made a mistake somewhere along the way. Here's the core of the problem, laid out as simply as I can manage. According to the standard model of cosmic history, the very first generation of stars, the true population 3 stars we discussed earlier, should have been built almost entirely from hydrogen and helium. Nothing else. No carbon, no oxygen, no nitrogen, none of the heavier elements that make up rocky planets or oceans or living things. Those heavier elements, the ones astronomers group together under the term metals, weren't supposed to exist yet, not in any meaningful quantity, this early in the universe's history. They needed time. They needed earlier stars to live and die and scatter their remains outward through violent supernova, seeding the surrounding gas with new material before the next generation of stars could inherit it. But Earendel formed, or at least appears to have formed, only around 900 million years after the Big Bang, In cosmic terms, that's still remarkably early. Early enough that, according to conventional models, there simply shouldn't have been enough previous stellar generations to enrich the surrounding gas with significant, heavier elements yet. And yet, buried within Earendel's spectrum, researchers found hints, debated, subtle, but persistent, suggesting a level of chemical complexity that theoretical models say shouldn't have been achievable yet, at least not to the degree the data seem to indicate. Imagine baking a cake using a recipe that calls for ingredients that, according to every record you have, hadn't even been invented yet at the time the cake was supposedly made. That's roughly the shape of the puzzle scientists found themselves facing. A star existing far earlier than heavier elements should have been common, showing chemical signatures that seem to require exactly those elements to already be present. Something in the timeline didn't add up cleanly, and nobody could simply wave that contradiction away. Here's the thing most people don't realize about how scientists respond to a finding like this. The instinct isn't excitement first, it's suspicion, directed inward at their own methods. Before entertaining any dramatic explanation, researchers first had to rule out every mundane possibility. Could the gravitational lensing itself be distorting the spectrum in some subtle, unaccounted for way? Could foreground galaxies sitting between Earth and Earendel be contaminating the light with their own chemical signatures, creating a false impression of complexity that wasn't actually coming from the ancient star at all? Could measurement uncertainty, inherent in analysing light this faint, this distant, simply be producing a misleading result? Each of these possibilities had to be carefully tested, modelled, and either ruled out or accounted for. And after that painstaking process, the anomaly, while not entirely free of uncertainty, refused to fully disappear. Something about Earendel's light kept suggesting a level of chemical richness that felt, to more than one researcher reviewing the results, almost impossible for an object this old, this early, this close to the theoretical dawn of stellar existence. There are a few possible explanations scientists have proposed, each one strange in its own particular way. One possibility is that Earendel isn't a single star at all, but a tightly bound pair, a massive primitive star locked in close orbit with a smaller, more evolved companion, one that had already lived, died and enriched its surroundings with heavier elements before Earendel itself finished forming nearby. Another possibility suggests that star formation in the extremely early universe simply happened faster and more efficiently than current models predict, allowing heavier elements to accumulate and spread more rapidly than anyone previously believed possible. A third possibility, quieter, more unsettling in its implications, suggests that our understanding of exactly how and when the universe's first generations of stars lived and died might simply be incomplete. Not wrong in some catastrophic way, but missing pieces, missing timelines, missing processes that haven't yet been fully identified or understood. Here's the thing most people don't realize about modern astrophysics. Even now, with instruments as extraordinary as Webb, there remain enormous gaps in our understanding of the universe's earliest chapters, gaps that a single strange discovery like this can suddenly uncomfortably illuminate. I want you to sit with that thought for a moment, quietly, in the dark. A star found at the very edge of observable time, behaving in a way that shouldn't quite be possible according to everything we thought we understood. Not a hoax, not a mistake, at least not one anyone has managed to identify despite careful, repeated scrutiny. Just a genuine, persistent anomaly, hiding in the light of an object 12.9 billion years old, quietly suggesting that the story of the universe's first stars might be more complicated, more surprising, and perhaps a little more mysterious than anyone had previously dared to assume. And once scientists began taking that anomaly seriously, another possibility crept into the conversation, one that reached beyond simple questions of chemistry and into something stranger still. What if Earendel wasn't truly alone out there in the darkness? What if something else, hidden, unseen, was sitting beside it this entire time, quietly shaping the very story we thought we understood? There's a particular kind of unease that comes from realizing you might not be looking at what you thought you were looking at. That feeling settled over the research team as they began exploring one of the more compelling explanations for Earendel's strange chemistry. What if this single point of light, magnified thousands of times by a fortunate gravitational alignment, wasn't actually a single star at all? What if, hidden within that one bright pixel of ancient light, two stars were quietly sitting together, locked in a close, invisible orbit, indistinguishable from one another, no matter how carefully Webb's instruments looked? This isn't as strange a possibility as it might first sound. Massive stars, the kind Earendel is believed to be, very often don't form alone. Throughout the universe, and likely throughout its earliest history as well, many of the largest, brightest stars form in close binary systems. Two stars born from the same collapsing cloud of gas, orbiting one another tightly enough that, from an enormous distance, they blend into a single point of light. Even with a telescope as extraordinarily sensitive as Webb, distinguishing two stars locked in a close orbit, separated perhaps only by a distance comparable to that between our Sun and its nearest planets, becomes essentially impossible at a distance of 12.9 billion light-years. Here's why that possibility matters so much to the mystery surrounding Earendel's chemistry. If a companion star exists, one that formed slightly earlier, lived a short, violent life, and exploded as a supernova before Earendel itself finished forming nearby, that explosion could have scattered heavier elements directly into the same region of space where Earendel was still developing. In that scenario, Earendel wouldn't necessarily be contaminated by some impossible, universe-breaking anomaly. It might simply be sitting unusually close to the aftermath of an earlier stellar death, absorbing trace amounts of material from a companion that briefly existed and briefly enriched its surroundings before Earendel's own light ever reached us. Think of it a little like finding unexpected ash and soot on a newly built house, only to eventually realize a small fire had burned in the exact same spot shortly before construction began. The unexpected material doesn't necessarily mean the house was built using some impossible process. It might simply mean something happened nearby, something brief and violent, just before the house went up. In Earendel's case, that something might be a companion star, born and destroyed in a cosmic instant, quietly seeding the region with the very elements that shouldn't have existed yet, according to the simplest possible timeline. But here's the thing most people don't realize about testing a theory like this. Confirming or ruling out a hidden companion star from a distance of nearly 13 billion light-years, magnified only by a fragile, temporary gravitational alignment, is extraordinarily difficult. Webb's instruments, as remarkable as they are, still can't directly resolve two individual stars sitting this close together at this distance. Instead, scientists have to rely on subtle clues buried within the spectrum itself. Small inconsistencies in brightness, temperature, or chemical signature that might hint at more than one source of light blending together into what appears, at first glance, to be a single point. Some of those subtle clues do appear to be present in Earendel's data, though researchers remain appropriately cautious about drawing firm conclusions from evidence this faint, this distant, and this difficult to fully untangle. It's the kind of finding that sits in scientific limbo for years, sometimes decades, waiting for either more sensitive future instruments or a slightly more favourable gravitational alignment to finally offer a clearer answer. For now, the companion star remains a compelling possibility rather than a settled fact, a shadow hidden just beyond the edge of what our current technology can fully resolve. And that uncertainty, rather than diminishing the story, somehow makes it feel even more haunting. Picture it for a moment. Two stars born together in the darkness of the early universe, locked in a close, silent orbit around one another. One of them larger, more volatile, burning through its fuel with terrifying speed before finally collapsing and exploding, scattering the very first traces of heavier elements into the space immediately surrounding its companion. And that companion, Earendel, continuing to burn steadily nearby, quietly absorbing the aftermath of its partner's violent death, long before either star's light would ever reach anyone capable of understanding what they were witnessing. If true, this scenario doesn't just solve a chemical puzzle, it adds an entirely new layer of narrative to an already extraordinary discovery. Earendel wouldn't simply be an ancient, isolated star drifting alone through the early universe. It might be a survivor, a witness to its own companion's destruction, carrying forward faint chemical traces of a death that occurred right beside it over 12 billion years ago, a quiet echo of violence, preserved not in memory but in light itself, patiently crossing the universe until it finally reached us. Here's the thing most people don't realize about how much uncertainty still surrounds even our most extraordinary discoveries. Science rarely offers perfectly tidy answers, especially when working at the absolute edge of what our instruments can detect. The companion star theory remains one of several competing explanations, alongside faster than expected early star formation and the possibility that our broader understanding of the early universe's chemical history is simply incomplete. What's certain is this: something about Earendel refuses to fit neatly into the story scientists expected to tell, and that refusal, that quiet, persistent contradiction, has forced astronomers to reconsider assumptions that had gone largely unquestioned for decades. For decades, the story of the universe's first stars was told with a kind of quiet confidence. Textbooks described it in clean, orderly stages. First, the cosmic dark ages, then the ignition of the first primitive stars, built purely from hydrogen and helium. Then their violent deaths, scattering the first heavier elements outward, slowly enriching the surrounding gas over hundreds of millions of years, until eventually, gradually, stars more like our own sun became possible. It was a tidy narrative, a clear step-by-step progression from simplicity to complexity. Earendel's strange chemistry threatens to blur every one of those clean, careful lines. Here's the thing most people don't realize about how scientific models actually work. They aren't discovered all at once in a single perfect form. They're built slowly, refined over decades, based on the best available evidence at any given time. Before instruments like Webb existed, scientists simply didn't have the ability to directly observe individual stars from the universe's first billion years. Their models were built on theory, on careful extrapolation, on physics we understood well applied to conditions we could only imagine. Earendel represents something rare and valuable: direct observational evidence from an era previously accessible only through calculation and inference. And that evidence is quietly complicating the tidy narrative scientists had grown comfortable with. If Earendel truly does show hints of heavier elements at an age where current models say those elements shouldn't yet be common, then one of several things must be true. Either heavier elements spread through the early universe faster than previously believed, perhaps through more efficient supernova, or through denser, more chaotic early star-forming regions than models currently account for, or the timeline for the universe's very first generation of stars needs to be pushed even earlier than currently assumed, giving more time for enrichment to occur before Earendel formed, or some combination of both possibilities along with factors nobody has fully identified yet. Think about what this actually means for the broader picture. It's not simply a matter of adjusting one small detail about one distant star. It potentially affects how we understand the entire sequence of cosmic chemical evolution, the process by which the universe transformed from a simple mixture of hydrogen and helium into the rich chemical diversity that eventually made planets, oceans, and life itself possible. A discovery like this doesn't just add a footnote to existing textbooks. It raises the possibility that an entire chapter needs to be reconsidered, rewritten, or at the very least, approached with far more humility than before. Here's the thing most people don't realize about how astronomers actually feel when a discovery like this emerges. There's genuine excitement, yes, but there's also a kind of productive discomfort. Nobody enjoys discovering that a well-established model might be incomplete, but most scientists will also tell you that discomfort like this is exactly how progress happens. Comfortable, unchallenged theories tend to stagnate. It's the strange anomalies, the stubborn contradictions that refuse to disappear, no matter how carefully they're checked, that eventually push understanding forward into genuinely new territory. And Arundel isn't entirely alone in raising these kinds of questions. Since Webb became operational, it has repeatedly detected galaxies from the early universe that appear more massive, more structured, and more chemically complex than existing models predicted. Some early galaxies observed by Webb seem almost too developed for how young the universe was when their light departed. Taken individually, each of these findings might be dismissed as an unusual outlier, an edge case, a measurement worth double-checking. But taken together, a pattern begins to emerge. A pattern suggesting that the early universe may have been more active, more chemically rich, and more rapidly evolving than the standard models, built before Webb's launch, ever anticipated. I want you to sit with that possibility for a moment, quietly, in the dark. It's easy to imagine scientific understanding as something fixed, something settled long ago and simply passed down through generations of textbooks. But the truth is messier, and in some ways, far more interesting. Our understanding of the universe's earliest chapters is still being actively written, revised and challenged, discovery by discovery, anomaly by anomaly. Arundel is one small ancient voice in that ongoing process, a single star whose faint, impossible light is quietly asking scientists to reconsider assumptions that, until recently, felt almost beyond question. Here's something worth remembering as we continue this journey together. Science doesn't move forward by being comfortable. It moves forward by encountering exactly the kind of quiet, persistent contradiction that Arundel represents, and refusing to look away from it. Every strange, unresolved detail in this star's light is, in its own way, an invitation. An invitation to build better models, ask sharper questions, and remain humble about how much of the universe's earliest history still remains genuinely unknown, even now, even with instruments as extraordinary as the one that finally allowed us to see this impossibly distant point of light at all. But understanding what this discovery means for our models of the universe is only part of the story. There's another layer to Arundel's existence, one that reaches beyond chemistry and physics into something far more difficult to fully grasp, the sheer, staggering emptiness that surrounded this star for most of its unimaginable existence. Before we return to the star itself, I want to take you somewhere quieter still, into the vast, echoing silence that filled the universe around Arundel, long before anything resembling a planet, a memory, or a single living thing had ever come into being. I want you to imagine, just for a moment, what it would actually feel like to exist in the universe Arundel was born into. Not the busy, star-filled sky you might picture on a clear night here on Earth, thick with galaxies, planets, and countless points of familiar light. Something far emptier, far quieter, a universe still mostly composed of dark, drifting hydrogen gas, punctuated only occasionally by scattered points of brilliance, the first fragile generations of stars, separated from one another by staggering, almost incomprehensible distances. Here's a number worth sitting with, At the time Earendel's light began its journey toward us, the universe was less than 1 billion years old. Today, it is nearly 14 billion years old. That means the light we're studying tonight departed when the universe had lived through less than 1/10 of its current age. Everything that would eventually fill the sky with familiar structure, most galaxies, most stars, nearly everything we associate with a rich, star-filled cosmos, hadn't formed yet. Earendel existed near the very beginning of that long, slow unfolding. Complete emptiness surrounded much of the space between those first scattered stars. Not emptiness in the way a quiet room feels empty, still filled with air, light, and countless small details. A deeper kind of emptiness. Vast stretches of space containing almost nothing but thin, cold hydrogen gas, drifting silently across distances that would take light itself millions of years to cross. No planets orbited these first stars in any confirmed sense we understand today. No moons reflected their light back into the darkness. Just isolated points of brilliance, burning fiercely and briefly, surrounded by almost nothing at all. Think about how different that is from the sky you might glance up at tonight. On a clear night, away from city lights, you can often see several thousand stars with your naked eye, part of a galaxy containing hundreds of billions more, itself just one of trillions of galaxies scattered throughout the observable universe. The universe Earendel inhabited had none of that richness yet. If you could somehow stand within it, looking outward in any direction, you might see only occasional isolated points of light, separated by darkness so vast, so complete, it would make even the loneliest stretch of ocean on Earth feel crowded by comparison. Here's the thing most people don't realize about just how much time passed before anything resembling our familiar universe took shape. Earendel's light left its source when the universe was under 1 billion years old. It has been travelling ever since for nearly 13 billion years, silently crossing a universe that spent almost that entire span slowly building itself into something recognizable. Galaxies merged and grew. New generations of stars ignited, lived and died, scattering ever more heavy elements outward. Planets began to form around some of those later stars. And through all of that immense unfolding, this single beam of light simply kept moving, undisturbed, carrying its ancient message forward through an ever-changing universe. Brutally isolated is perhaps the best way to describe existence in that earliest era. No radio signals passed between distant points of light, because nothing yet existed capable of producing them. No signs of structure, no hint of anything beyond simple scattered stars burning against an overwhelming backdrop of darkness. If Earendel had a companion, as some researchers suspect, the two of them may have represented one of the only sources of light within an enormous surrounding volume of otherwise empty space. Two small candles burning alone in a room larger than the mind can properly hold. And yet, within that overwhelming emptiness, something extraordinary was quietly happening. Each of those isolated, scattered stars was slowly building the raw materials for everything that would eventually follow. Fusing hydrogen into helium, and in some cases forging heavier elements deep within their cores. When they died, often in violent, brilliant explosions, they scattered those elements outward into the surrounding darkness, slowly, gradually, enriching the vast emptiness around them. It would take hundreds of millions of years, and countless generations of stars living and dying in that same lonely process, before the universe accumulated enough heavier material to eventually build planets, oceans, and life. Here's the thing most people don't realize about their own existence when you trace it back far enough. Every atom of carbon, calcium, and iron inside your body was forged inside a star. Not necessarily Earendel itself, but stars very much like it, burning brightly and briefly within that same early empty universe, before dying and scattering their contents outward into the darkness. In a very real sense, the emptiness surrounding Earendel wasn't simply a void waiting to be filled. It was the beginning of a process that, billions of years later, quietly patiently, eventually led to you. I want you to hold on to that feeling for a moment. The vastness, the silence, the almost unbearable scale of time and space involved before we return to Earendel itself. Because understanding just how empty, how isolated, and how young the universe still was when this star's light began its journey makes what happens next even more striking. Somewhere within that immense echoing silence, the light we're studying tonight kept moving, carrying its secrets forward, unaware that nearly 13 billion years later, it would finally arrive, somewhere capable of understanding what it had witnessed. And that understanding comes with an unsettling truth of its own, one we need to confront directly. There's a truth about Earendel that we've touched on already, but haven't fully sat with. I want to slow down here, because this is one of those ideas that, once it truly settles in, changes the way you look at every point of light in the night sky. When you look at any star, you are never seeing it as it exists right now. You are always seeing the past. For nearby stars, that past might only be a few years old, barely a delay at all. But for Earendel, that past stretches back nearly 13 billion years. And that gap between what we see and what actually exists today carries an unsettling implication. Massive stars, the kind Earendel is believed to be, do not live long lives. This is one of the strange, almost paradoxical truths of stellar physics. The bigger and brighter a star is, the faster it burns through its fuel, and the shorter its total lifespan tends to be. Our own sun, comparatively modest in size, is expected to shine steadily for roughly 10 billion years. A star like Earendel, potentially dozens or even hundreds of times more massive, might survive for only a few million years before exhausting its fuel entirely. A few million years compared to the nearly 13 billion years its light has already been travelling toward us. Do the math with me for a moment and let the answer really land. If Earendel lived for even a generous few million years, and its light left nearly 13 billion years ago, then the star itself almost certainly reached the end of its life, an almost incomprehensibly long time ago. Long before Earth existed, long before our sun existed, long before the Milky Way galaxy had finished forming into anything resembling its current shape. Whatever remains of Earendel today, if anything at all, has looked completely different for longer than most of cosmic history has existed. Here's the thing most people don't realize about what stars like this typically become once their brief, brilliant lives come to an end. Massive stars often die in catastrophic explosions called supernovae, briefly outshining entire galaxies before collapsing inward, sometimes leaving behind an incredibly dense remnant known as a neutron star, or in more extreme cases collapsing further still into a black hole. If Earendel followed this typical path, then somewhere out there, in a location we can no longer directly observe, its remains may now exist as a black hole. A place where gravity is so extreme that not even light itself can escape. Think about the strange irony contained within that possibility. We are studying, in extraordinary detail, the light of a star that may have transformed, billions of years ago, into an object defined entirely by its complete absence of light. Earendel, once one of the brightest points in its region of the early universe, may now exist as one of the darkest objects the universe can produce. The very light we're analysing tonight, capable of revealing so much about this star's temperature, size and chemistry, is a message from a version of Earendel that likely no longer exists in any recognisable form. Complete transformation, on a scale that's difficult to fully absorb. Not simply aging or dimming gradually the way you might imagine an ember slowly cooling. A total, fundamental change in what this object even is. From brilliant, blazing star to potentially one of the most extreme, light-devouring objects known to physics. And all of that transformation happened silently, invisibly, somewhere in the depths of the early universe, long before its light ever reached anyone capable of understanding what they were witnessing. Here's the thing most people don't realize about how astronomers actually think about this kind of delay. It doesn't diminish the value of the discovery. If anything, it deepens it. We aren't simply looking at a distant star, we're looking at a preserved fragment of cosmic history, a snapshot frozen in light, capturing a single moment from an object that has since undergone changes so extreme we can barely conceptualize them. Studying Earendel isn't like studying a living creature. It's closer to studying a fossil, an imprint left behind by something that existed briefly, then transformed into something else entirely, long before we ever knew to look for it. And yet, that fossil still tells us something real, something true. The physics governing that ancient light hasn't changed, even if the object producing it has transformed beyond recognition. Every detail scientists extract from Earendel's spectrum, its temperature, its estimated mass, its puzzling chemical signatures, remains a genuine, accurate record of a moment that truly happened, nearly 13 billion years ago. In that sense, this light functions almost like a message in a bottle, cast into the vast ocean of space at the dawn of time, drifting for billions of years, until finally, against extraordinary odds, it washed ashore here, on a small planet orbiting a star that hadn't even been born yet when the message was first sent. I want you to hold both of these truths together for a moment, quietly, in the dark. Earendel, as it exists in this ancient light, feels almost alive to us. A single point of brilliance we can study, question, and marvel at, and yet, the true current fate of whatever remains of that star is almost certainly something else, entirely. Something dark, distant, and utterly transformed. It's a strange kind of ghost story, told not through folklore, but through physics. A story about how something can vanish so completely, and yet still leave behind a message capable of crossing the entire history of the universe to reach us, long after its own ending. For all that Webb has managed to reveal about Earendel, I want to be honest with you about something important. This story doesn't end with a neat, tidy conclusion. Real scientific discovery rarely does, especially when working at the very edge of what our instruments can detect. Even now, years after this star was first confirmed, astronomers continue to debate, refine, and question many of the details surrounding it. What we have isn't a finished picture, it's an unfolding one, still missing pieces, still inviting more questions than it has managed to answer. Here's the thing most people don't realize about the limits of even our most advanced technology. Webb, remarkable as it is, still cannot directly resolve Earendel into anything more than a single point of magnified light. It cannot take a true photograph of the star's surface. It cannot definitively confirm, beyond reasonable doubt, whether a companion star truly exists nearby, contributing to the puzzling chemical signals researchers have detected. Every conclusion drawn about Earendel comes from careful, indirect analysis, comparing faint patterns of light against decades of theoretical models, built from stars we can observe far more clearly, much closer to home. That indirect approach comes with real limitations. Gravitational lensing, the very phenomenon that made this discovery possible in the first place, also introduces its own uncertainties. The exact amount of magnification depends on extremely precise assumptions about the mass and structure of the galaxy cluster responsible for bending Earendel's light. Small adjustments to those assumptions could shift estimates of the star's true size, brightness, and even its exact distance. Scientists have refined these calculations repeatedly since the initial discovery, and while the broad picture has remained consistent, some of the finer details continue to be debated, tested, and occasionally revised. There's also the matter of exactly how to interpret the chemical signatures hinted at within Earendel's spectrum. Not every research team studying this data agrees on how significant or how certain these signals truly are. Some analyses lean toward genuine evidence of unexpected chemical complexity. Others suggest the anomalies might be explained by measurement uncertainty, subtle lensing distortions, or contamination from foreground objects sitting between Earth and Earendel, rather than representing something truly unusual about the star itself. This kind of careful, ongoing disagreement isn't a weakness in the science. It's exactly how legitimate scientific progress works, slowly, skeptically, through repeated testing rather than premature certainty. Here's the thing, most people don't realize about how astronomers actually feel about this uncertainty. Rather than being frustrated by unanswered questions, many researchers find them exciting. An unresolved mystery, like Earendel, represents an open door, an invitation for future observations, future instruments, and future generations of scientists to push even further than current technology allows. Every unanswered question becomes a target for tomorrow's research, a reason to keep building better tools and keep looking more carefully at the same patch of ancient magnified light. And there's real reason for hope that clearer answers may eventually arrive. Gravitational lensing events, like the one magnifying Earendel, aren't necessarily permanent or unchanging. As the galaxy cluster responsible for the lensing continues its own slow motion through space, the precise alignment could shift over time, potentially altering the degree of magnification in ways that might reveal new details or confirm existing suspicions. Future observations, planned for years to come, may offer sharper, more detailed data than what was available during Earendel's initial discovery. Beyond Earendel itself, astronomers are actively searching for similar objects, other individual stars from the universe's earliest chapters, magnified by their own fortunate gravitational alignments, waiting somewhere in Webb's vast catalogue of observations to be identified. If more of these ancient, isolated stars can be found and studied, scientists will finally have something Earendel alone cannot provide: a broader sample, a wider comparison, allowing researchers to determine whether Earendel's strange chemistry represents a genuine anomaly or simply one example of a pattern that turns out to be far more common throughout the early universe than anyone previously suspected. Here's the thing, most people don't realize about how much remains genuinely unknown, even in an era of telescopes as extraordinary as Webb. We have, in many ways, only just begun exploring the earliest chapters of cosmic history in this kind of direct, detailed way. Earendel represents one of the very first individual glimpses humanity has ever managed to capture from that distant, formative era. There will almost certainly be more discoveries like it, stranger, older, or perhaps even more contradictory, waiting to be found as our instruments and techniques continue to improve. I want you to sit with this unfinished quality for a moment, rather than rushing past it. It would be easy to want a clean, definitive answer, a tidy explanation that resolves every question Earendel has raised. But the honest truth is quieter, and in some ways, more beautiful than that. We are living through the very beginning of humanity's ability to study the universe's first stars directly. Earendel isn't the final word on that story. It's closer to the opening line, ancient, mysterious, and only partially understood, inviting us to keep listening, keep questioning, and keep looking upward into a darkness that still holds far more secrets than answers. I want to bring this back to you now, not just to Earendel, not just to distant physics and ancient light, but to the simple, quiet fact of your own existence, lying here, listening to this story in the dark. Because everything we've explored tonight, the first stars, the long silence of the early universe, the violent deaths that scattered heavy elements outward into empty space, isn't really separate from you. It's the beginning of your own story, told on a timescale so vast it's easy to forget you're part of it at all. Here's the thing. Most people don't realize about the atoms that make up their own bodies. the calcium in your bones, the oxygen you're breathing right now without even thinking about it, the iron carried through your blood with every heartbeat. None of these elements existed in the earliest universe. They didn't exist when Arendel's light first began its journey. They had to be forged, painstakingly, inside the cores of stars like Arendelle, and then scattered outward through catastrophic explosions, before ever becoming available to form anything as complex as a planet, an ocean, or a living, breathing person. Think about what that really means. Somewhere in the deep, ancient past, long before Earth existed, a star very much like Arendelle lived its brief, brilliant life, and then died in a burst of light bright enough to briefly outshine entire galaxies. In that explosion, elements were forged that would later, over billions of years, drift through space, gather together, and eventually become part of a planet, part of an ocean, part of you. In a very real, very literal sense, you are made from the remains of stars that burned and died long before the sun ever existed. This is sometimes called stellar nucleosynthesis, though you don't need to remember that term. What matters is the simple, staggering truth it represents. Every atom heavier than hydrogen and helium in your body was forged inside a star. You're not simply looking up at the night sky when you gaze at the stars. You're looking at your own distant, ancestral origin, written in fire, scattered across billions of years, and eventually assembled, almost impossibly, into someone capable of understanding where they came from. Here's the thing most people don't realize about why Arendelle's discovery feels so quietly profound. It isn't just a record-breaking distance or an interesting anomaly in stellar chemistry. It's a direct physical connection to the very beginning of the process that eventually created you. When Webb captured that ancient light, it wasn't simply photographing a distant object. It was capturing a fragment of the same cosmic story that led, step by step, generation by generation, star by star, all the way to this exact moment, to you lying quietly in the dark, listening to a description of your own origins. And there's something else worth sitting with here, something almost paradoxical. Arendelle and stars like it existed in a universe so young, so early, that nothing resembling life could have possibly existed anywhere yet. No planets had fully formed, no oceans existed, no possibility of biology, consciousness, or thought had yet emerged anywhere in the entire universe. And yet, within the violent deaths of stars just like this one, the very ingredients required for all of that to eventually become possible were quietly being created, scattered outward into the darkness, patiently waiting across billions of years for the right conditions to finally assemble them into something capable of curiosity, into something capable of building a telescope and pointing it back toward its own beginning. There's a strange, beautiful symmetry contained within that idea. The universe spent billions of years creating the conditions necessary for consciousness to exist. And once that consciousness finally emerged here, on this small, quiet planet, one of the very first things it chose to do was build an extraordinary machine, launch it nearly 1 million miles into space, and use it to look back at the ancient starlight responsible for its own creation. Webb isn't simply a scientific instrument. In a very real sense, it's the universe, having finally developed the capacity for self-awareness, turning around to study its own origins. Here's the thing most people don't realize about what it truly means to look up at the night sky. You're not simply observing distant, unrelated objects, separate from your own existence. You're looking at your own family history, written across an almost incomprehensible span of time and distance. Every star, every galaxy, every faint point of ancient light carries within it some small part of the same process that eventually led to you, standing here, capable of understanding, capable of wonder, capable of quietly marveling at just how extraordinary, how impossibly unlikely your own existence truly is. Earendel's ancient, contradictory light isn't just a puzzle for scientists to solve. It's a mirror reflecting something deeply personal back at anyone willing to really look closely. A reminder that the universe's oldest, strangest secrets aren't separate from your own story. They are your own story, told on a scale so vast it's easy to forget, until a moment like this one, quiet, dark and thoughtful, brings it gently back into focus. We've travelled a long way together tonight, all the way back to the very beginning of time itself, through hundreds of millions of years of absolute darkness, into the birth of the very first stars, and finally to a single, fragile point of light that crossed nearly the entire history of the universe just to reach us. Earendel, a star, or perhaps two stars, burning briefly and brilliantly in a universe still learning how to exist, its light carrying secrets that scientists are still, even now, quietly trying to fully understand. Here's the thing most people don't realise about what makes this story so remarkable. It isn't simply that we found a distant, ancient star. It's that we found it at all. Out of the entire observable universe, trillions of galaxies, countless billions of stars, scattered across unimaginable distances. One single point of light happened to align, by pure chance, with a massive galaxy cluster in exactly the right way, at exactly the right moment, to become visible to a telescope built by creatures who wouldn't even exist for another 13 billion years. The odds of that alignment feel almost too precise to be believable, and yet, here we are. Think about everything that had to happen for this moment to exist at all. A star had to form, in one of the very first generations the universe ever produced. It had to grow massive enough, bright enough, to eventually be detectable across almost unimaginable distances. A vast cluster of galaxies had to form directly between that star and a small, otherwise unremarkable planet, bending its light with just enough precision to magnify it thousands of times over. And on that small planet, a species had to evolve, develop curiosity, build civilizations, develop science, and eventually construct one of the most sophisticated machines ever created. Launch it nearly 1 million miles into space and point it to exactly the right patch of sky at exactly the right time. Every single step in that chain feels almost impossibly unlikely on its own. And yet, taken together, they happened. They actually happened. You are living in the exact moment in cosmic history when all of those improbable conditions finally aligned, allowing humanity to catch a direct glimpse of light from the universe's earliest, most mysterious chapter. Not a simulation, not a theoretical model, an actual physical beam of ancient light, captured, measured, and studied, carrying real information across nearly the entire span of cosmic time. Here's the thing most people don't realize about why moments like this matter so deeply, beyond the science itself. We are, each of us, made from the same material forged inside stars, just like Earendel. We are built from stardust, quite literally, elements created inside ancient furnaces of nuclear fusion, scattered outward through violent stellar deaths, gathered together over billions of years into planets, oceans, and eventually into something capable of wondering where it all came from. When you study a star like Earendel, you aren't simply studying a distant, unrelated object. You are studying your own deep cosmic ancestry. There's a phrase some scientists like to use, one that captures this idea beautifully. We are the universe noticing itself. Think about what that really means. For nearly 14 billion years, the universe existed without anyone to observe it, without anyone to measure its light, calculate its age, or wonder about its origins. And then, through an almost unbelievably long, patient process of stellar death and rebirth, atoms gathered together in just the right way, on just the right planet, to eventually become curious, to eventually build telescopes, to eventually look outward, and for the first time in the universe's long history, begin to understand its own story. You are part of that story. not separate from it, not simply an observer standing outside looking in, but a genuine, physical continuation of the very process we've spent this entire journey exploring together. The same universe that created Arendelle, that scattered its light across billions of years of darkness and silence, eventually created you as well. Different in form, different in scale, but built from the exact same fundamental material, shaped by the exact same ancient, patient forces. Thank you for spending this time with me tonight, drifting together through the deepest, strangest chapters of cosmic history. We've travelled further than most people ever pause to consider, all the way back to the edge of time itself, and returned with something quietly extraordinary. Not just facts about a distant star, but a deeper sense of how connected you truly are to everything you see when you look up at the night sky. If tonight's journey brought you even a small sense of that wonder, consider leaving a like or subscribing, so more curious minds like yours can find their way here too. The next time you find yourself outside, late at night, looking up at that quiet, scattered field of stars, I want you to remember Arendelle. Remember that some of that light left its source before Earth even existed, travelling patiently through billions of years of darkness, just to reach your eyes at exactly this moment. You are not separate from that vast ancient story. You are its continuation. Sleep well tonight, knowing that you carry the universe's oldest light within you. Keep looking up at the stars. Good night.